In 1946, French engineers finished a steam locomotive so advanced it could unleash nearly 5,500 horsepower, yet it was so complex that only one ever ran. Mechanics called it a nightmare, but its designer called it perfection. It was built to rescue a nation's broken railways when even American diesels were too costly to import. Why gamble everything on a single, unrepeatable machine? The answer begins with the incredible story behind its creation. Its official name is as precise as its engineering: SNCF 242A1. It was not just another locomotive in a long production line, it was a singular machine, born from both necessity and ambition, carrying a designation that French railway workers would remember for decades. The numbers in its name told a story. 242 referred to its 484 wheel arrangement, a format reserved for only the most powerful express engines. A 1 signified there would never be a second. What set the 242A1 apart was not just its rarity, it was the raw force contained inside its frame. Test reports from the late 1940s recorded outputs between 5,230 and 5,430 horsepower, and rounded up the headline figure was 5,500 horsepower. This was more power than any other steam locomotive in Europe, and nearly double what most famous British or American engines could muster. Where others strained, the 242A1 surged forward, pulling trains of over 1,000 tons at speeds that rivaled the fastest passenger services of its day. The locomotive was rebuilt from an earlier prototype, the EST 241101, but Chapelon's modifications made it almost unrecognizable. It was longer, heavier, and bristling with experimental features. The massive boiler ran at 280 pounds per square inch, feeding a system of 4 compound cylinders that extracted work from steam again and again before letting it go. Each component was engineered for one purpose: to squeeze every last bit of energy from coal and water and turn it into relentless forward motion. There was only one 242A1 ever built. It spent its working life based at Le Mans, running the 411 kilometers to Brest. Its existence was an open challenge to the world. What if steam could be pushed further than anyone had dared? The answer depended on whether the world was ready to meet the demands of a machine this powerful and this unforgiving. By the end of World War II, France's railways lay in ruins. Allied bombing and retreating German forces left behind a shattered network, with hundreds of bridges and tunnels destroyed, rail yards gutted, and thousands of locomotives and wagons missing or damaged beyond repair. Freight traffic crawled through bottlenecks, where viaducts had been patched together in weeks instead of months. Passenger trains limped across the country, slowed to a crawl by temporary repairs and the constant threat of breakdowns. The National Railway, SNCF, faced a daunting reality. Imports of American diesel locomotives, the kind that had transformed U.S. railroads during the war, were simply out of reach. Foreign currency reserves were depleted, and every franc had to be stretched across the vast demands of national reconstruction, including bridges, factories, power stations, and housing for millions. In this climate, each major purchase was scrutinized by government officials balancing the need for rapid recovery against the limits of a battered treasury. Mass production of reliable, easy-to-maintain locomotives was the logical answer for most countries. But France's industrial planners and engineers saw a different path. Instead of conceding to foreign technology, they doubled down on French ingenuity and technical independence. For them, importing expensive diesels was not just a financial burden, it was a blow to national pride and self-reliance. So SNCF turned to its own talent pool, searching for a way to leapfrog the competition without draining the treasury. The challenge was to build a locomotive powerful enough to pull heavy trains across a damaged network, using the resources and expertise already available at home. The result was a bold wager, pouring limited funds into a single ultra-advanced prototype that could, in theory, outperform anything else on the rails. That gamble was not without risk. The cost to build just one of these experimental engines rivaled what it would take to produce several conventional locomotives. Yet for post-war France, the prospect of restoring rail service with a homegrown marvel of engineering was worth the investment. SNCF's planners were not chasing spectacle for its own sake. They were betting that radical innovation could deliver practical results when the country needed them most. André Chapelon's life was defined by a single question: how far could steam power really go? He was not content to accept the limits that others saw as fixed. In the workshops and drafting rooms of post-war France, Chapelon studied every wasted calorie, every stray puff of steam, searching for ways to turn loss into motion. His notebooks were filled with calculations about thermodynamics, fluid dynamics, and heat transfer equations, each one a step toward a locomotive that could convert more of its fuel into speed than any before. The foundation for his masterpiece was the EST 241-101, a three-cylinder express engine built before the war. Where others saw a dead-end prototype, Chapelon saw raw potential. He stripped away the old design and reimagined it as a four-cylinder compound machine. This meant steam would be used 4 times in sequence, passing from high-pressure to low-pressure cylinders and extracting energy at every stage. Such a system demanded absolute precision, the timing of each piston, the routing of every pipe, and the careful management of heat and pressure. Any imbalance would waste energy, or worse, damage the engine. To Chapelon, efficiency was more than a technical goal. It was a philosophy, almost a moral calling. He wrote about the wastefulness of traditional steam engines with frustration and even anger, convinced that with the right design, France could outpace the rest of the world using coal and water alone. His approach was holistic. He considered not just the cylinders and boiler, but the shape of the exhaust, the treatment of the water, and the very arrangement of the locomotive's wheels and axles. Each change was calculated to reduce friction, recover lost energy, or balance the immense forces at work inside the machine. The result was a locomotive that bore little resemblance to its predecessor. It was longer, heavier, and bristling with innovations that only a handful of engineers could fully understand. For Chapelon, the 242A1 was not just a machine. It was proof that the steam age could be pushed further, that perfection was possible if one refused to compromise. His ambition would drive the project into uncharted territory, setting the stage for engineering feats and challenges that no railway had faced before. Steam entered the 242A1's boiler at 280 pounds per square inch, far higher than most locomotives of its era. But power was not just about pressure. The real breakthrough came in how that steam was used, not once but 4 times across a sequence of cylinders. This was compound expansion, taken to its absolute limit. The process started with 2 high-pressure cylinders, each carefully sized to extract the first burst of energy. As the steam expanded and cooled, it was routed into a pair of much larger low-pressure cylinders for a second, third, and even a fourth stage of work. Each transfer squeezed out more motion, making sure almost nothing was wasted. The dimensions of these cylinders were calculated down to the millimeter, small for high pressure, massive for low pressure, so that the energy curve matched the locomotive's needs at every speed. This 4-stage cycle meant that the steam's journey was a tightly choreographed dance. Each piston had to move in perfect harmony, with timing set so that the force from one cylinder did not cancel out or overload another. The crank angles, valve events, and steam paths all had to sync with almost no margin for error. Even a slight misalignment could throw off the rhythm, dropping efficiency or risking damage to the engine. The result was an engine with extraordinary power density. On the test bench, the 242A1 delivered over 5,000 horsepower from a single boiler, a feat unmatched by any other European steam locomotive. But this complexity came at a cost. The phasing of 4 cylinders under different pressures demanded constant attention from the crew, and the mechanical precision required for everything to work smoothly was beyond anything found in ordinary railway workshops. This was not just a machine, it was a living equation, running at full speed with every moving part solving for maximum efficiency in real time. 3. Chimneys rise from the top of the 242A1, each one engineered to exacting standards. This triple exhaust was not for show. It was a calculated response to the problem of back pressure, the resistance that builds up as steam tries to escape the cylinders. In a conventional locomotive, too much back pressure chokes the engine, wasting energy and limiting power. Chapelon's solution was to split the exhaust into 3 precisely shaped stacks, each tuned to handle its share of the flow. The result? A measured reduction in back pressure by nearly 12%. That single innovation allowed more of the engine's power to reach the wheels, instead of being lost as heat and noise. At the heart of this system sat the Kill-Chap double blast pipe, a marvel of fluid dynamics but one that demanded perfection. The position and diameter of each nozzle had to be set within a millimeter. If the geometry drifted out of alignment, even by the smallest amount, the draft through the firebox would falter. That meant less air for combustion, weaker steam production, and a sudden drop in horsepower. Test charts from the workshops of SNCF showed just how quickly performance could collapse if the blast pipe was even slightly off. For the maintenance crews at Le Mans, this was a daily concern. Adjusting the Kill-Chap meant crawling into the smoke box with feeler gauges, checking and rechecking tolerances that most mechanics never had to think about. The entire exhaust system was a balancing act, one that left no room for error. When perfectly tuned, the triple chimney and double blast pipe worked in concert to pull hot gases through the boiler at astonishing speed, keeping the fire fierce and the steam supply steady. But the same sensitivity that unlocked record-setting power also created a new kind of vulnerability. A single misaligned nozzle, a warped gasket, or a buildup of soot could tip the system out of balance. For the men tasked with keeping the 242A1 running, it was a constant reminder. This was not a locomotive you could simply patch up and send back out. Every detail mattered, down to the last millimeter. Water was the silent threat lurking beneath the SNCF 242A1's gleaming exterior. For most steam locomotives, any nearby supply, river, tank, or municipal pipe would do. But this engine treated ordinary water like poison. Its high-pressure boiler and compound cylinders demanded a level of purity that few rail depots in France could guarantee. Even a trace of minerals left behind as steam condensed would begin to form scale, a thin stony crust inside the boiler tubes. Over time, this scale acted like a thermal blanket, choking off heat transfer and throwing the locomotive's finely balanced thermodynamics into chaos. Depot engineers at Le Mans soon learned that a single millimeter of scale could slash heat transfer by as much as 20%. Efficiency would collapse, and the engine's legendary power would fade. Worse, scale buildup risked hotspots, areas where metal overheated, warped, or even cracked under pressure. For the 242A1, a machine running at 280 pounds per square inch, that was a risk no one could afford. To keep the engine safe, SNCF invested in dedicated water treatment facilities at select depots. Water had to be softened, filtered, and chemically dosed before it ever reached the tender. This hidden infrastructure came with its own costs, chemical tanks, pumps, and the constant labor of checking pH and hardness. Logbooks from the era record daily tests and careful dosing routines, rituals that were as critical as oiling a bearing or checking a valve. The The result was a locomotive that could only run on routes where treated water was available. A missed refill or an untested supply could sideline the whole operation. For the mechanics, this meant living with a constant edge of anxiety. Every fill-up was a gamble, every boiler washout a race against invisible deposits. The 242A1's demand for purity limited its world to a handful of prepared depots, and every journey depended as much on chemistry as on coal. The engine's raw power was only possible because of an invisible web of infrastructure, hidden behind the scenes and maintained by engineers who understood that a cupful of untreated water could undo years of innovation. On the test tracks outside Le Mans, the SNCF 242A1 revealed its true nature. Official records from 1950 to 1952 show the locomotive hauling trains that would have crippled most engines of its day. More than 1,000 tons of rolling stock pulled at speeds that defied expectations for steam. During one celebrated run, the drawbar registered over 4,000 horsepower, a figure that left engineers and observers in disbelief. The locomotive's dynamometer car, packed with SNCF officials and skeptical experts, recorded a sustained output that matched or exceeded the latest electric engines then coming into service. Speed was no less impressive. In controlled trials, the 242A1 reached 158 kilometers per hour, nearly 98 miles per hour, on level track with a full train behind it. Regular testing approved operational speeds up to 130 kilometers per hour, a threshold that only the most advanced express services in Europe could claim. Even at these velocities, the locomotive's compound expansion system and triple chimney exhaust delivered a steady, relentless surge of power. The test sheets from these runs, stamped and filed at SNCF headquarters, became legendary among engineers. A single steam engine, rebuilt from a pre-war prototype, had outclassed the best efforts of rival nations. Every metric told the same story. Whether it was the raw tonnage moved, the horsepower measured at the drawbar, or the stopwatch timing over long stretches of mainline, the 242A1 delivered results that seemed almost impossible. For a brief moment, Chapelon's vision was vindicated, not as a theory, but as a roaring, thundering fact. The locomotive had done what it was built to do, set new records, and proved that steam in the right hands could still lead the world. SNCF's boardroom minutes from the early 1950s read like a quiet verdict on the 242A1's fate. The cost to build this single locomotive equaled that of 3 reliable workhorse engines already in mass production. Every franc spent on Chapelon's masterpiece meant one less locomotive for the rest of France's battered rail lines. While the 242A1 dazzled engineers with its performance data, financial officials saw only the bottom line, a machine so advanced and so expensive that it could never be replicated at scale. At the same time, the National Modernization Plan was gathering momentum. SNCF's leadership, under pressure to restore dependable service across thousands of kilometers, had begun to channel investment into electrification and diesel procurement. Policy memos from the Ministry of Transport outlined a future where overhead wires and diesel engines would replace steam entirely. The 242A1, for all its brilliance, was already a relic before it reached its prime. Workshop ledgers and procurement records tell the rest of the story. The locomotive's maintenance costs, the specialized water treatment infrastructure, and the need for a cadre of expert mechanics made it an outlier in a system designed for standardization. By 1960, SNCF's rolling stock was dominated by new electric and diesel units. The 242A1 was withdrawn from service and quietly scrapped. Its experimental legacy preserved only in technical reports and the memories of those who had seen it run. In the end, the locomotive's greatest achievement was also its undoing. It had proven steam could be perfected, just as the world decided it no longer wanted perfection in steam. Today, as railways chase simplicity and automation, Chapelon's masterpiece stands as a reminder. Engineering brilliance alone does not shape the future. Timing and practicality do. The 242A1 proved what is possible, yet it vanished because the world had already moved on. Innovation's fate often hinges less on genius than on what the moment demands. Sometimes the best ideas arrive just one era too late.